A thin plate of uniform thickness is subjected to pressure as shown in the figure below. Under the assumptions of plane stress, which one of the following is correct? The options are normal stress is 0 in the Z direction, normal stress is tensile in the Z direction, normal stress is compressive in the Z direction, and normal stress varies in the Z direction. This question is being asked in 2014 GATE set 2 for 1 mark. Here you can see a circular plate. Okay, let us see the assumptions of plane stress. What is plane stress actually? Plane stress is also called as biaxial state of stress. That is, the state of stress is defined in two particular axes. That is a simple definition of plane stress. Here you can see the assumptions as one of the three dimensions is very small. Here you can see the thickness is very small compared to the diameter, which forms x and y axis dimension, while the z axis dimension, that is thickness, is very small. And the second assumption is that loading in smaller dimension direction is very small. Here you can see no loading is done on the Z direction. No loading is there on Z direction. So also if there is loading, it is considered to be very small, and eventually the stress comes out to be 0 in the Z direction. So the answer here is normal stress is 0 in the Z direction. Similarly, the shear stress is also considered 0 on the Z face, that is tau x, Z, tau yz, tau zx, and tau zy all comes out to be 0. If the Poisson's ratio of an elastic material is 0.4, the ratio of modulus of rigidity to Young's modulus is. They have given mu, that is Poisson's ratio of an elastic material, and they have asked the ratio between G, that is modulus of rigidity, and Young's modulus E. First, we must know the different relationships between elastic constants. These are constants derived through experiments. This question is being asked in 2014 1 mark set 4. Okay, let us know the relations. It is related to Young's modulus, as that is the shear modulus or rigidity modulus is related to the Young's modulus as E is equal to 2G into 1 plus mu. Similarly, the bulk modulus K is related to Young's modulus as E is equal to 3K into 1 minus 2 mu. Also, without having mu, a relation between E, K and G is E is equal to 9K G by 3K plus G. These three relations are sufficient, and from this you can derive this relation. These three relations are sufficient to find a third elastic constant by the values of the given two elastic constants. Here we are given 0.4, that is simply 0.4 is being given and the ratio is asked. So it is simple to just substitute 0.4 here and you will be getting G into 2.8 is equal to E. So G by E comes out to be 1 by 2.8, which is 0.35 to 0.36. The state of stress at a point is given by sigma x is equal to minus 6 megapascal. That is normal stress in x direction as minus 6 megapascal and in y direction as 4 megapascal. That is compressive and this is tensile, and tau xy is minus 8 megapascal. Minus refers to anti-clockwise shear. The maximum tensile stress at the point. Whenever the maximum tensile stress at the point is being asked, the thing we have to determine is the major principal stress, that is sigma 1. Sigma 1, as we have already studied, sigma 1 formula is 1 by 2 into sigma x plus sigma y plus root of sigma x minus sigma y whole square plus 4 tau xy squared. If in case they have asked the minimum tensile stress or the minor principal stress, here instead of plus we have to replace it by minus. So just by substituting minus 6, 4 and minus 8 for tau xy, we will be getting the answer as 8.4339 megapascal. It is a simple 2 mark question being asked in set 1 of GATE 2014. A 200 millimeter long stress-free rod at room temperature is held between two immovable rigid balls. Here you can understand that it is held between two fixed supports. That is similar to a fixed beam, an encasted beam, a built-in beam. The temperature of the rod is uniformly raised by 250 degrees Celsius. If the Young's modulus and coefficient of thermal expansion are 200 gigapascal and 1 into 10 power minus 5 per degree Celsius respectively, the magnitude of longitudinal stress in megapascal developed in the rod is. They have asked longitudinal stress. As I have said earlier, that if the stress is possible, then the only condition is that it must be restricted, that is completely restricted expansion. Here it is between two immovable rigid walls, so it comes under for completely restricted expansion. Here thermal stress and longitudinal stress both are same. This is developed due to the restriction of the strain due to thermal. That is, if you restrict the thermal strain, you will be getting a longitudinal strain which results in a thermal stress or longitudinal stress. The formula, as we have discussed earlier, it is alpha into del T into E. Here they have given us uniformly raised by 250 degrees Celsius. That is, it is not increased to 250 degrees Celsius. It is increased by 250 degrees Celsius. That is, for example, if it is at 0 degrees Celsius, it is increased to 250 degrees Celsius. If it is at 25 degrees Celsius, it is increased to 275 degrees Celsius. So 250 degrees Celsius is the difference. So alpha into del T into E. Alpha is 1 into 10 power minus 5 into del T is 250 into E 200, comes out to be 500 megapascal. A rod is subjected to a uniaxial load within linear elastic limit. When the change in the stress is 200 megapascal, the change in the strain is 0.001. If the Poisson's ratio of the rod is 0.3, the modulus of rigidity is. They have asked G by giving the values of Poisson's ratio and the change in stress and change in strain. It is not just stress and strain. When you see a stress strain curve, there you can see the slope as Young's modulus. Young's modulus is nothing but the slope between the stress strain curve, where stress forms the y-axis and strain forms the x-axis. So the slope becomes dy by dx, which is d sigma by d epsilon. So d sigma here it is 200 megapascal and d epsilon is 0.001. If you substitute, you will be getting the Young's modulus. We know that just by having two elastic constants, we can find a third elastic constant. Here we are given Poisson's ratio, which is 0.3, and here we have calculated the Young's modulus. Using this E and mu, you will be calculating G. So the G comes out to be 76.9230 gigapascal. The principal stresses at a point inside a solid object are sigma 1 is equal to 100 megapascal, sigma 2 is equal to 100 megapascal, and sigma 3 is equal to 0 megapascal. The yield strength of the material is 200 megapascal. That is SYT is 200 megapascal. The factor of safety calculated using Tresca's theory, Guest and Tresca's theory, that is maximum shear stress theory, MSST. NT, and the factor of safety calculated using Van Mises or Van Mises and Henke's theory or MDET theory or maximum distortional energy theory is NV. Which one of the following relations is true? They have established a relation between the factor of safety calculated through Tresca theory and the factor of safety calculated through maximum distortional energy theory. Here you can see the relations as options. We have to find the actual relationship in this particular case. This question is being asked in 2016 set 1 gate question for 2 marks. Okay, first let us know the MSST failure criterion. This is the failure criterion. If this particular value exceeds this value, the material fails. Similarly, if this total value exceeds this particular value, the material fails. So these conditions are said to be the failure criteria. Okay, in the case of MSST, maximum, that is absolute maximum shear stress is being found by this formula, sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 1 minus sigma 3 by 2. Here you can see the sigma 3 comes out to be 0. If it is 0, then it becomes a biaxial state of stress. So these are the only two principal stresses acting. So here you can confine to this sigma 1 minus sigma 2 by 2 or sigma 1 by 2 or sigma 2 by 2. But here you can see both are like in nature. So you have to go for sigma 1 by 2. If it is sigma 1 by 2, the maximum tensile stress is 50. And here you can see this is shear stress. So this must be lesser than or equal to shear yield strength by the factor of safety. But according to MSST, there is a relation between SYS, that is shear yield strength, and strength in tensile yield, as SYS is equal to SYT by 2. So comparing this and this, you will be getting the NT to be 2. According to Tresca theory, the factor of safety for this condition, you will be getting 2. Similarly, if you substitute, this is biaxial state of stress failure criteria. If it is for triaxial state, I have discussed earlier. So here, just by substituting this sigma 1 and sigma 2 values and SYT as 200, you will be getting NV, which also comes out to be 2. So NT is equal to NV. Just by knowing this failure criteria, keep in mind this sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 1 minus sigma 3 by 2 is being applied. If you apply, you will be getting sigma 1 minus sigma 2 by 2 and sigma 3 is 0. So it will be sigma 2 by 2 and sigma 1 by 2. So eventually from this triaxial, you will be getting the biaxial failure criteria. So 100 by 2 is lesser than or equal to SYT by 2 means 100 by NT. So NT comes out to be 2. Similarly, if you substitute here you will be getting NV equal to 2. So NT is equal to NV is the answer. The state of stress at a point on an element is shown in figure A. The same state of stress is shown in another coordinate system in figure B. They have given the images here and they have asked for the components tau xx, tau yy and tau xy. This question is being asked in 2016 for 1 mark in set 3 gate paper, mechanical paper. Okay, here you can see the option says A, B, C and D as P by root 2 minus P by root 2. So you have to determine tau xs, tau xy and tau yy. Okay, they have given this is the actual loading condition. So this represents a particular plane, that is a point and a particular plane in this element. If you consider this as an element, this as a particular plane, you can understand that this plane is at 45 degree to this actual loading condition. So from this loading diagram, you can understand that there is no shear stress acting externally. So this plane comes out to be the principal plane and this plane comes out to be the principal plane. Both are principal planes and always tau max planes are at 45 degree to the principal planes. To this principal plane, this comes out to be the tau max plane. So tau max planes are always complementary in nature. That is, if you less 45 degree, you will be having tau max plane here, and if you add 45 degree, you will be having tau max plane here. So these both are tau max planes, that is maximum shear stress planes. Normal stress in that maximum shear stress plane is always calculated as the average of the principal stresses, sigma 1 plus sigma 2 by 2. As you can see, in normal stress, why we are finding here the normal stresses, because they have asked the tau xx and tau yy. Tau is actually used to denote the shear stress, but here they have used for the normal stress denotion. So sigma 1 plus sigma 2 by 2 gives P by this area divided by P by this area plus minus of P by this area, because this is compression. So this comes out to be 0. So tau xx and tau yy comes out to be 0. Whereas tau max is calculated using this formula, sigma 1 minus sigma 2 by 2. This can be visualized as a Morse circle. In this special case where you can see the applied load is like one is compression and the other one is tension and of equal magnitude. So in that particular case, the Morse circle will have the center at the origin. Here you will be having the principal stresses relation as shown here. Sigma 1 is equal to minus sigma 2. So if you substitute here, you will be getting P by area minus of minus P by area. So it will be P by 2. So you'll be getting the load as P. Here we are not considering the area. We have taken it as unit T. So just by putting P, you'll be getting P as the answer. So you'll be having tau xx, tau yy as 0 and tau xy as P. In the engineering stress strain curve for mild steel, the ultimate tensile strength UTS refers to yield stress, proportional limit, maximum stress, and fracture stress. These are all the points in a stress strain curve. This question is being asked in 2017 GATE set 1 for 1 mark. Okay, let us understand these points. What is a yield stress? Yield stress is a particular value of stress above which yielding, that is, the material begins to deform plastically. And what is proportional limit? It is a limit up to which Hooke's law is valid. Many of you may confuse it with elastic limit, but actually up to proportional limit only this linearity, that is the Hooke's law, is possible. Beyond that, there is a curvy nature which gives the end of elastic limit. But in certain MCQs, there may be elastic limit as the only option. In such cases, you can go for elastic limit. But the most appropriate one is proportional limit. And what is UTS? UTS refers to the maximum stress that can be withstood by the material. That is, even though it begins yielding, it can withstand up to this value only. Fracture stress is the final value at which the material breaks. That is, it gets cut. If it is mild steel, it gets cut into a cup and cone fracture. So from this you can understand that UTS refers to the maximum stress. So C comes out to be the answer. The Poisson's ratio for a perfectly incompressible linear elastic material is. They have given the options, and this question is being asked in 2017 1 mark in set 1. Okay. Let us know the different conditions where we will be having different Poisson's ratio. For perfectly incompressible, perfect plastic or perfect elastic material, mu is 0.5. This is because in the case of perfect plastic material and perfect elastic material, and also in perfectly incompressible material, the volumetric strain comes out to be 0. So for the volumetric strain to be 0, mu must be 0.5. Okay. In the case of cork, you will be having the mu as 0. That is, though there may be a longitudinal strain, the lateral strain is 0. It is a special case. Okay. In the case of foam, the Poisson's ratio is -1. Generally, for metals, the Poisson's ratio considered is 0.25 to 0.33. That is, from 1/4 to 1/3. For rigid bodies, mu is not defined. There is a discussion, broad discussion in this area, but rigid bodies rigid bodies do not come under strength of materials, because strength of material deals with elastic bodies, deformable bodies. So, if we consider the Poisson's ratio, we know the Poisson's ratio as negative of the lateral strain divided by longitudinal strain. But in rigid bodies, there is no longitudinal strain. So, longitudinal strain is 0. Eventually, the lateral strain also comes out to be 0. It is -0/0. 0/0 is an indeterminate form. So, it is generally for rigid bodies, Poisson's ratio is not defined. Generally, for engineering materials, mu value ranges from 0 to 0.5. But if they haven't mentioned about engineering materials, there is a possibility for mu to range from -1 to 0.5. This is sufficient to answer this question. So, you can understand that for perfectly incompressible linear elastic material, the Poisson's ratio is 0.5. A rectangular region in a solid is in a state of plane strain. Remember that plane strain and plane stress conditions are different. the x, y coordinates of the corners of the undeformed rectangle are given by. This is the initial coordinates of the rectangle which has been shown here. And the rectangle is subjected to uniform strain epsilon xs. That is, in x direction it is subjected to a strain of 0.001 and y direction 0.002, and the shear strain is 0.003. They have asked the deformed length of the elongated diagonal. That is not just the strain of the diagonal. They have asked the deformed length, which means actual length, that is original length plus change in length, up to 3 decimal places in units, because they haven't given any millimeter or metric units. So they have just mentioned a generic term of units. Okay, the rectangle, this is drawn by understanding the question. Remember that this pic is not given with the along with the question. So this question is being asked in 2017 GATE set 1 for 2 marks. Okay, first we have to draw the rectangle, and from this rectangle you can determine the original length of the diagonal by these values 4 and 3. By Pythagorean rule you can understand that this value comes up to be 5, and from this value you can calculate the theta, that is the plane of the diagonal. Okay, by determining the angle of the diagonal you can determine the strain happening in the diagonal plane. So you have to know these values epsilon x, epsilon y and gamma xy, which have been given in the question. So just by substituting these in this, remember this, just by replacing normal stress by normal strain and shear stress by shear strain by 2, you can get this equation. Or else just by replacing epsilon n by sigma n and gamma xy by 2 by tau xy, you can get the equation for epsilon n theta, that is normal stress at a plane whose angle is theta. Okay, here you can find the epsilon n theta. Generally strain is defined as change in original dimension divided by original dimension, that is change in dimension divided by original dimension. So just by multiplying this epsilon n theta with the original dimension, that is by 5, you will be getting the change in dimension. So after finding the change in that diagonal length, you just add this with 5, which is the original length, and you will be getting the deformed length of the diagonal. As you can see, the answer comes out to be 5.0154, which is greater than this 5. So it is being elongated. Remember, also there is a possibility of getting constricted, that is it may get reduced in size. So this change in length will be negative sign. When you find this epsilon and theta, there may be a negative sign, and if there is a negative sign and the original length minus the change in length, you will be getting the diagonal length as less than this 5.